On the British coast, there's a $58 billion fortress being built. This is Hinkley Point C, the most expensive nuclear power plant ever built. It's Europe's largest construction site, Britain's first nuclear reactor in 33 years, and when it finally turns on, it will power 6 million homes and produce 7% of the nation's electricity. But to survive, it needs 11.6 million cubic meters of seawater every single day. That's enough to fill an Olympic pool every 18 seconds. And with that water comes a threat no concrete can stop. It isn't terrorists, it's fish. This is the story of how one of the most expensive megaprojects in history became hostage to fish worth more than their weight in gold. To understand why the UK is accepting this financial pain, you have to look at the alternative. Right now, the British energy grid is walking a tightrope. The old nuclear stations are shutting down. They're old and tired. And while wind and solar power are great, they have one big problem. They don't work when the wind stops blowing and the sun goes down. That's where Hinkley Point C comes in. This isn't just another power station. It's a baseload monster that produces 3,200 megawatts of electricity and runs 24/7. When those two reactors finally turn on, they'll generate enough electricity to power 6 million homes. Think about that. 7% of the entire nation's electricity will come from this single spot. But the stakes here are bigger than just keeping the lights on. This project is a test. After a 33-year gap, Britain has forgotten how to build nuclear power plants. The factories closed down. The welders retired. The engineers moved on. Hinkley Point C was supposed to be the big comeback. Instead, it has become a warning. Because if this project fails, the entire plan to get Britain to net zero carbon emissions falls apart. The location of this battleground was chosen carefully. Hinkley Point sits on the Somerset coast. It's next to the empty shells of two old, dead nuclear plants. The power lines are already there, and the ocean provides an endless supply of that critical cooling water. But turning this corner of England into a nuclear fortress required a massive effort. The site is currently the largest construction project in Europe. It covers 430 acres. It's so big it has its own bus fleet, hospital, and police force. There are 14,000 workers there right now. They work day and night, battling the rain and the mud to build 2 EPRs. European pressurized reactors. These are the most complex machines ever designed to boil water. They have double-layered concrete walls and safety systems that are backed up 3 or 4 times. But this ambition caused a problem. 3 decades without building had eroded every part of the nuclear industry. They didn't have the supply chain, welders, the inspectors, or the engineers. They effectively had to import an entire nuclear industry from scratch. And as the engineers soon discovered, the hardest part was the water. Now let's understand the mechanics of the problem. Nuclear power is a simple way to boil water. You split atoms, you create heat, you make steam, and that steam spins a turbine. But once that steam has done its job, it needs to be turned back into water so it can be cycled through again. To do that, you need to cool it down. That is why, beneath the seabed, 3 massive tunnels have been bored through rock. 2 of these tunnels are for intake. They stretch 3 kilometers out into the ocean, sitting 30 meters beneath the waves. At the end of these tunnels are massive concrete intake heads. Every single day they suck in an ocean's worth of water. And when that water is spat back out, it's about 10 degrees warmer than the rest of the bay. But the real problem happens at the intake. The Severn Estuary is officially designated as a special area of conservation. It is teeming with protected species like Atlantic salmon, Thwaite shad, and river lamprey. When you turn on a vacuum cleaner this powerful in a protected ecosystem, you create a death trap. The water enters the pipe with huge velocity. Fish get pulled in. If they hit the mesh screens, the pressure pins them there and they die. If they get sucked through the screens, they travel through the plant's cooling loops and get boiled. This creates a double threat. For the environmentalists, it violates the strict EU Habitats Directive that protects these waters. But for the engineers, it's a safety risk. If millions of fish clog the intakes, the flow of water stops. If the water stops, the reactor can't cool, and if the reactor can't cool, you have to shut down this machine instantly. According to regulations, you cannot operate this plant unless you prove you won't destroy the ecosystem, and solving that problem would prove harder than building the reactor itself. Now, everything about Hinkley Point C is huge. Take the foundations. When they poured the base for the first reactor, it was the largest concrete pour in British history, beating the record set by the Shard in London. They poured 9,000 cubic meters of nuclear-grade concrete non-stop to create a seamless slab. But because British safety rules are extremely strict, they had to change the design 7,000 times. They ended up using 25% more concrete and 35% more steel than the exact same reactor in France. The walls are thicker, and the reinforcement is denser. To move all this weight, they couldn't use normal cranes. They had to build the world's largest crane called Big Carl. It stands taller than the towers of the Golden Gate Bridge. It runs on 6 kilometers of rail tracks, gliding between the buildings like a mechanical dinosaur. It can lift 5,000 tons in a single go. This machine changed the game. Instead of building the reactor piece by piece in the wind and rain, engineers built massive rings inside weatherproof bunkers. Then Big Carl would roll over, pick up the entire ring, and drop it into place. This allowed them to hit massive milestones. In December 2023, they lifted the first dome. Then, in December 2024, they installed the reactor pressure vessel, the 500-ton steel heart of the plant. That was a historic moment. It was the first time a new nuclear reactor had been installed in Britain since 1991. And in July 2025, the second dome was lifted into place. Right now, the project is shifting gears. The heavy lifting is mostly done. Now comes the fit-out. And there's good news. Because they learned so many hard lessons on the first reactor, Unit 2 is being built about 20% to 30% faster. But while the engineers were finally finding the rhythm, the project was losing money on a problem nobody saw coming. This brings us back to the fish. Back in 2013, the plan was to stop fish from entering the tunnels through acoustic fish deterrent. This was a disco for fish. 280 underwater loudspeakers that would blast sound pulses to annoy the fish and scare them away from the intakes. But the Bristol Channel is a brutal environment. The tides are fierce and the visibility is zero. EDF argued that sending divers down to maintain these speakers was a suicide mission. It was too dangerous. So they tried a plan B. They proposed creating 800 acres of new salt marsh nearby to breed new fish to replace the ones the plant would kill. The problem with salt marsh was that it required flooding farmland. Back in 2013, there was no better option. Technology hadn't caught up. But by 2025, ceramic transducers had matured enough to offer a third solution. It sounded like a fair trade until the locals realized what that meant. It meant flooding productive farmland and destroying villages to create a swamp. Years of farmer opposition culminated in a November 2024 review that broke the internet. The report claimed that this entire acoustic system would cost nearly £700 million, and statistically, it would save one salmon every 12 years. Now, to be fair, that number is a statistical abstraction known as adult equivalent salmon. The system would save thousands of smaller fish, but in the court of public opinion, the damage was done. The headline was, "Britain spends $1 billion to save one fish." It became a symbol of everything wrong with modern infrastructure: regulatory paralysis, skyrocketing costs, and a complete loss of common sense. Under immense pressure, the engineers pivoted. In March 2025, they committed to ceramic transducers. These are modern, low-maintenance sound projectors that can be fixed from a boat without sending divers to their deaths. The final system, including the new sound projectors, special low-suction intakes, and a slide that flushes caught fish back to sea, will still cost around $900 million. But while the engineers were finding their rhythm, the project was losing money on problems that compounded the original challenges. The 33-year gap had already crippled the British supply chain. Then Brexit in 2020 made everything worse. Supply chains were snarled. Then COVID-19 caused a 15-month delay. But the real hidden cost was that they were still paying for the learning curve. They had to retrain 8,000 workers in new centers of excellence just to learn the basics of nuclear construction again. They were paying for the learning curve. Add in the skyrocketing cost of steel and global inflation, the budget exploded. In 2016, this plant was supposed to cost $18 billion, which has now exploded over 3 times. So, after all the drama, delays, and the billions spent on fish, what does Britain get? The impact of Hinkley Point C will be profound. When those reactors turn on, they'll power millions of homes. It reduces the country's dependence on imported gas, giving Britain a level of energy security it hasn't had in decades. But the impact goes beyond electricity. Thousands of British companies are now nuclear qualified. Economically, the project has pumped $16 billion directly into the British economy. And for the locals? The project has poured $25 million into the community. The plant even has its first station director, Nicola Fauvel, who is already leading the Ghost Crew, the team preparing to take the keys and run this machine. But there is a sting in the tail. Someone has to pay for that $58 billion price tag. And that someone is the British public. The electricity from Hinkley will be expensive, significantly more expensive than current wind or solar power. Because of government contracts signed years ago, bill payers will be topping up the difference for decades. Estimates suggest the public could pay an extra $65 billion over the plant's life. We're paying a premium for reliability. The question is it a price worth paying? Today, Hinkley Point C is racing toward the finish line. Unit 1 is expected to turn on between 2029 and 2031. The government is already using the hard-won lessons from this project to approve the next one, Sizewell C, hoping that copying the design will finally bring the costs down. But the One Salmon scandal has triggered a massive rethink in the UK. We're seeing a shift in the national conversation. The debate is moving from save every single fish at any cost to a harder question. How do we balance nature with the desperate need for clean energy? When you look at Hinkley Point C, it's easy to see a disaster of budget overruns and delays. It's easy to laugh at the billion-dollar fish disco. But zoom out and you see something else. You see a country trying to rebuild its industrial muscle after letting it atrophy for 30 years. You see the immense difficulty of decarbonising a modern economy. It has been messy and expensive. But in a few years, when the lights turn on in 6 million homes, that $58 billion price tag will look like a bargain. Because in the world of megaprojects, the only thing more expensive than building it is not having it when you need it most. But we want to hear from you. Do you think the price of this reliability is worth the cost? Or should Britain have invested those billions elsewhere? Let us know in the comments below. And if you want to see more stories like these, make sure to subscribe to MegaBuilds. Thank you for watching.